Hi guys, today we're going to do a review of frequency translation. That is, how do you change one frequency to another. We're also going to have a look at the different modulation techniques such as SSB, FM, AM and CW, and also some digital modes as well. Okay, so for the frequency multiplier, basically any oscillator that you create will actually not produce a perfect sine wave, will also contain something called harmonics. Now harmonics are integer multiples of the fundamental frequency. So for example, if we had a 7 megahertz oscillator, then it would also produce harmonics at 14, 21 and 28 megahertz. Now, by deliberately distorting the signals, these harmonics can actually be amplified, okay, and then you pass it through a band pass filter, and then you can actually remove the other frequencies you're not interested in. So, for example, if you distort the harmonics of a 7 megahertz oscillator, maybe using a diode or something like that on the output, you're going to get an increase in the amplitude of the harmonics. But then all you need to do is then get a bandpass filter, and then filter out the band that you are only interested in. So, for in this case, 21 megahertz or the 15 meter band can be produced from 7 megahertz or the 40 meter band. You can use something called a frequency multiplier. A Class C amplifier can actually be used to produce integer harmonics, such as times 2, times 3, times 4. Okay, and also the full wave rectifier can be used to double the frequency. But these methods will not work on AM or SSB. Remember, a Class C amplifier will only really reproduce the frequency and then multiples of. Okay, it can't deal with the amplitude of the waves. So if you're trying to create a higher frequency with FM or CW, this is one way that you could do it. You can also use the full wave rectifier. Here's a diagram of the full wave rectifier, but using two diodes and a centrally tapped transformer. It still works exactly the same way as the four diode mechanism as well. Basically, the frequency that comes out is twice that of the frequency going in. You could possibly use a flip-flop if you needed to divide the frequency, although this is fairly rare for radio purposes. But if you wanted to half the frequency, you could use a frequency divider, such as a flip-flop. But you're going to end up with also harmonics, so you'd have to have a bandpass filter just to remove anything. Next, slightly more complicated but very clever, is something called the phase-lock loop frequency synthesizer. Essentially, how a phase-lock loop works is you have a reference oscillator that doesn't change. Okay, so that would probably be based on a crystal, and then a second oscillator that's completely vary in frequency, and you have a process of checking the phase of the two waves and of the two different oscillators, and by comparing the phase of the two waves, you can ensure that the frequency of the variable frequency oscillator is remained stable. Okay, so a variable frequency oscillator, the great thing about it is it can have any frequency possible. Okay, but they're naturally unstable. So how do you maintain the stability? Well, you compare it against a reference oscillator. So here's a diagram of what actually happens. The voltage controlled oscillator may have a frequency of several times that of the reference oscillator. So you can see in the feedback there's a phase detector that will compare the phases of the two different waves. But before that, there's a divide by n counter. So if you wanted to have a output frequency that was, say, twice that of your reference frequency, you'd divide by 2. So if you had 7 megahertz reference crystal, okay, in your voltage controlled oscillator, you'd divide by 2. Then what would happen is there'll be a process of feeding back. So how could you the phase be, or how could the wave be in phase? Well, what you want is you want two 7 megahertz frequencies coming into the phase detector. So that means that the voltage controlled oscillator will be changed by the phase detector up to 14 megahertz. Okay, and then the 40 megahertz is divided by 2. Okay, if that's what you want, divided by 2, going back into 7 megahertz, and then the two 7 megahertz signals are compared. One very, very useful piece of equipment is something called a mixer. A mixer, there's several different forms of a mixer, but in this case, in the diagram here, you have two centrally trapped transformers, one with a signal input and a signal output, and then a oscillator input as well. But really, all you need to be aware of what a mixer does is essentially it takes two frequencies, okay, it combines them, produce the sum and the difference of the two frequencies. So if you had a 18 megahertz and 2 megahertz input into a mixer, okay, what would you end up producing? Well, you could produce the sum, so 18 plus 2 is 20 megahertz, or the difference, 18 minus 2, is 16 megahertz. So either of these two output frequencies can be filtered out as needed. So if you had a 18 megahertz and 2 megahertz source, you could end up making 20 or 16 megahertz, and then just filter out which one. In fact, you'll end up making both of them at the same time. You just filter out the one that you don't need. Now, the good thing is a mixer can be used with all types of signals. So AM, sideband, and even audio signals. So if you wanted to make a very, very simple what we call dual sideband transmitter, you could have audio on one input and an oscillator on the other, and the mixer would mix the two signals together and produce two sidebands. You could then filter out one of the sidebands and hey, you just made a single sideband radio. Okay, chapter 21, we're going to look at modulation methods. So basically, what is modulation? Well, it's the process of adding some kind of information to an electronic carrier signal. So a carrier signal would be very, very high in frequency, the radio signal. You have to change something about it to impart information onto it. So that change could be frequency or the amplitude. Excuse me. Or even something called the phase, which is kind of beyond the scope of this course. Now, with amplitude modulation, you're changing the size of the carrier waves to impart the information of the audio wave onto it. So your carrier wave is very, very high in frequency. So, for example, if you listen to Cape Talk, 567 megahertz, I think it is. Sorry, not megahertz, kilohertz. Okay, so that's a very, very high frequency signal, and then you impart onto it your audio, and the audio will increase and decrease the size of the carrier. Now, it's not very efficient way of transmitting information. In fact, it's very, very poor. 50% of the power always has to go to the carrier. And if you look at the final diagram, you see the central carrier, but now rather than looking in the time domain, we're looking in the frequency domain. And you see there's something called the upper and lower sidebands, and this is where your audio information is actually imparted in the upper and lower sidebands. Now, we don't actually need one of the sidebands. They are mirror images, and therefore, they contain the same information. So one of them is not needed as well. So 75% of all the power used in AM is completely useless. Well, the first thing we could do is remove we could remove the carrier. This is probably the easiest thing to do with a balanced mixer. So basically what you do is that now you've removed your carrier, and you can now have the upper and lower sidebands, and the 100% of the power shared between the sidebands. The circuitry to receive this is much more complex than AM receiver, because you have to put the carrier back in somehow. So not particularly easy circuit to create, although it's completely possible. Sorry, excuse me. But But still, both the sidebands contain both the same information, so again, it's pointless really transmitting both of them. Now, really, what you want to do is have the upper or lower sideband. Now, in amateur radio, from 10 megahertz upwards, we traditionally use the upper sideband, and then lower than 10 megahertz, so lower than 30 meters, so or a wavelength bigger than 30 meters, so 40 and up to 40, 80 megahertz, 80 meters, 60 meters, 180 meters, or 160 meters, sorry. All those bands use lower sideband, and then from 30 meters or 100 or 10 megahertz upwards uses the upper sideband. It's just the standard. There's no reason really for it. You could easily transmit lower sideband in the upper higher frequencies. You just won't make many contacts because most people won't know what you're doing. Okay, so what's the advantage of sideband? Well, basically the spectrum is much less, okay, and allows really much more space. You can fit basically more channels or more areas for people to transmit. Also, all your power is only on the information imparted, okay, and something you can't have as much fading will occur. Because when you previously in AM you had a carrier wave, with something called superposition, if the carrier wave reflects off something, it'll actually end up cancelling itself out, and it'll actually end up producing no signal. So in some cases, AM can cancel itself out, whereas this is not possible with when you're just transmitting just one sideband. It's not possible. So all your power is basically dedicated just to one of the sidebands if you're using single sideband. Now, sideband does have a disadvantage, and the disadvantage is that with tuning, when you tune an AM signal, the radio locks onto the carrier and it knows what is 0 hertz, okay, well, what's the lowest possible frequency. With upper or lower sideband, that information has been destroyed. Okay, so you have to tune very finely in order to get the person's audio sounding correctly. Otherwise, you sound like either Barry White or Donald Duck. But it's not a particularly difficult thing to do. You just have to be careful with tuning, and that's the only disadvantage, really, I would say, with sideband. Continuous wave, or also known as Morse code, okay, is basically when you're just either transmitting or not transmitting one single frequency. Okay. So just by interrupting the signal using the Morse code rhythms of the different letters, you can impart information onto the wave. Now, FM is slightly different in that you are modulating the frequency of the carrier. So the actual the carrier is moving side by side, side to side in the frequency domain, but in the amplitude it is not changing at all. Okay. Now the advantage of FM is that most natural interference is to do with amplitude, not variations in frequency. So FM is very is not susceptible to natural interference as much as AM. If you're ever in a lightning strike or thunderstorm, tune your radio to AM and you'll hear of the lightning strikes. In FM, that's not possible. You can't hear it because there's no change in frequency. And then finally, well, there's a plethora of digital modulation techniques. You can have something called phase shift key or frequency shift key, amplitude shift keying. There's lots and lots of different things where you can impart digital information onto a signal. Some of the most common ones, well, PSK31 about 10 years ago is very, very popular, but it seems to be no longer in vogue. FT8, or Fun Times 8, as I like to call it, is very popular at the moment. It has incredible error correction. And can be heard up to 26 decibels lower than the noise level. That's 400 times weaker than the ambient noise around you. So they're incredibly efficient. effectively, the working, I always describe it a bit like a laser beam, in that what you are doing is you are reducing the bandwidth, so all the energy of your transceiver, rather than going, if you're using voice, that energy of maybe your 100 or 50 watt transmitter is going to an area of about 2.7 kilohertz. But if you're using a digital, it becomes much, much narrower. Maybe a few hundred hertz is all that's needed to impart the FT8 information. And that means that your energy is concentrated like a laser beam. So if the band is slightly open, those signals will get through, whereas audio will really kind of struggle. Okay, I hope that's been useful, and yeah, bye for now.